Hey ho, everybody! All right, so I decided to redo this video because the last 2 or 3 times I tried it, I blathered on and I yammered on and I misused a couple terms. Um, I also used a term which has two different meanings in Unity. So I realized that even one of my tutors got confused on the term that has two different meanings. So it's probably best if I don't actually use the term. uh, well, I'll tell you what the term is, but I'm not going to use it. Viewport. There are like 2 or 3 different uses of viewport, and in the Unity docs. In fact, in a previous Unity version, viewport is listed more than once in the inspector, and it caused a lot of confusions with me in terms of the walkthrough. So I'm not going to focus on the Unity docs being broken. I'm not going to focus on the Unity itself refusing to fix problems that it should fix, or has claimed that it's not going to fix. I'm just going to tell you when Unity is, which things don't actually function. They may function in a later update. Right now I'm using the update that was available in December of 2022, even though it's 2023 right now. And that's because the most recent Unity update is broken in a lot of ways that I don't want to deal with. So for my projects, I'm not using the update that was released, last month? Or a month and a half ago? I lose track of time. Instead, I'm just going to talk about Pixel Perfect. What is the definition of Pixel Perfect? And the fact that there are 3 definitions of Pixel Perfect. And how not to let it confuse you. Basically, your goal, if you're going for pixel art in a Unity project, you have to decide, what are you doing? Are you doing retro pixel art or retro themed pixel art? Retro pixel art means that you are copying or replicating the limitations of pixel art for a specific build of machine. And that could be, I'm going to do pixel art that was featured in the arcades in 1984. So you're probably going to look up arcade machines. Now, arcade machines, you could fudge quite a bit because different arcade machines came out in 1984, different cabinets. Every single arcade cabinet featured a different build or of a motherboard, right? But if you're going for consoles, then you can absolutely know the limitations of a console. So arcade machines is like, are you going to do an arcade machine like Pac-Man? Are you going to do an arcade machine like Galaga? Are you going to do an arcade machine like Sinistar? Yeah, I know. They're probably, I just said 1984, but we're talking about different years here. And that's my point. Like, the different arcade cabinets have different capabilities. They were focused on different things. You could fudge it a little bit. But in general, you would get a concept of what you're going for. Like, I'm going to build a game that's very much like Sinistar, so I'm going to examine the build of Sinistar machines, and I'm going to limit myself to their limitations, right? So you're not going to see like super 3D graphics. Or I'm going to make a game that's like Tempest, so I'm going to use Vectrix graphics, right? Vector graphics, like the Vectrix. That is actually a little bit more difficult in Unity. Unity's not really built to do vector graphics. But I've seen people actually manage a simulation of it. So that's pretty cool. I actually kind of want to learn how to do that. So I am going to make a game that's based off of vector graphics in the near future. Or, I'm going to build using NES rules. The rules that govern the NES. But then you have to decide, are you going to use the later chipset or the early chipset? That sort of thing. And either way, what you are doing is you're going to build rules that focus on the limitations or presentation of the CRT, cathode ray tubes. And so this is what this first section of the video is going to be about. Now that I've gotten my introduction out of the way, at the 6-minute mark, a big reveal. Technology Connections, one of my favorite people on YouTube. I want you to look at the screen for a second. I'm going to stop talking just for about 10 seconds. I want you to look at the screen and look at the header and absorb the information you're getting from the header. My viewers are not suspicious to the fact that I had to break up a little cat fight in my room or in my house. Oh wait, the mic's on. Hot mic moment. Yeah, I had to get up and I had to take care of 2 kitties. But I also wanted you to look at this. Now, what do you see there? That is the grid for one type of CRT. It's really one of the most common grids, right? If you don't know what CRTs are, CRTs, cathode ray tubes. And I'm going to be as unscientific and as cool as I could possibly be by saying it used to be a long time ago in the galaxy. Well, I hate Star Wars now. Actually, I've hated it since '98. Freaking racist Jar Jar Binks. Okay, so let me get on to let me restart here. Once upon a time in a kingdom far, far away, Americans, people, humanity, world over, used a form of vision transportation. This vision transportation occurred in a box, and it showed you images from lands far away by zapping a screen full of brilliant phosphors. And how was it zapped? Why, with lasers, of course! So, that's as technological as I'm going to get. Magic little elves used laser guns to zap at people's eyes, but they were blocked by a magical screen of phosphor, and that gave us images of distant lands. I'm as right as I am wrong. And, but we're going to stick with my story of lasers, because lasers are cool. So, the whole thing here, and it is a big thing. What do those things look like? Well, first of all, you see a grid. And the grid is what houses the elements that get zapped by the lasers. And you see that they're red, green, and blue pockets in the screen that is offset and absolutely not pixel perfect. You know why it's not pixel perfect? Because television resolution is not equivalent to pixels. So, if you're going for pixel perfect, you have to decide, are you actually going for square by square perfect? Are you going for programming perfect? And programming perfect is mostly what we're talking about when we're talking about Unity. Or are you going for CRT pixel perfect? So I guess we're really kind of sort of talking about three concepts here. Although in reality, when you're on the programming side, you're talking about two concepts. And the two concepts are fitting pixels next to each other to avoid tearing. And that's the best term that I could use to describe it. If you're familiar with the term tearing, then graphical tearing, then you understand what I'm talking about. If you're not familiar, let me look it up for you. Screen tearing, or graphical tearing, occurs when your monitor's refresh rate and GPU's frame rate are not synchronized. It's characterized as a horizontal split at one or more places in the image. You can fix it by enabling VSync, etc., etc., etc. So that's the... Oh, let me move it over. Let me move it over and things so you can read it. Screen tearing occurs when your monitor's refresh rate... Yeah, okay, so you get that. Another form of tearing is it gives the same effect. Let's see if we can see this. Let's see if it shows an example of tearing. Oh, there's tearing right there. You see how it's kind of offset? You know, it looks weird. Another form of tearing occurs when, for whatever reason, the a circular object, like a circular CG object, just is not, it doesn't, it's jagged. That's another example of tearing, is when the circular, like you have a smooth object and it's jagged. And, you know, if you've ever like had, this is horizontal, mostly horizontal tearing that they're showing. But there is like issues where the CG model or the resources just overcome the resources of the processor. And I guess most people just refer to it as aliasing, like you have to turn the aliasing on or anti-aliasing on, because the objects are aliased from the rest of the what have you, right? Okay, so basically it's like graphical deformations. Well, pixel tearing, I've decided that's the best way to describe it. It's what happens when you have, and let me have Paint, let me bring up Paint here. Let me look at Microsoft Paint. So you have two objects that are made out of pixels, right? Here's a box, and it's drawn like a pixel. Or it's just a square, and it's made of like a bunch of little pixels, right? All these little pixels, kind of like bricks that build a house. All these little pixels, blah, 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 blah. And you have another sprite over here, and that's full of pixels. Pixel, 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 pixel. Well, if you program the wrong type of resolution, when you stick these two together, what you might actually wind up with is, instead of the box being big like this, next to the other box, providing a seamless thing, what you wind up is the box is suddenly shorter. And then maybe you have another box here which is a little bit wider, and it overlaps. Well, this is caused by fat pixels or skinny pixels. And that's when the pixels cannot be multiplied to be perfect squares. Because despite my rectangles here, a pixel is a square. And that's another kind of a rectangle. There we go, that's squarish. And when you don't multiply it by a factor of 2 or a factor of 4, usually I use a factor of 4. Because a square has 4 sides. It limits the opportunity for errors. But because every once in a while I run into errors with pixels that I multiply by a factor of 2. Probably shouldn't happen, but it does. It's rare, but it does. Well, if you don't multiply it by a factor of 2, let's say you multiply it by a factor of 3, what you wind up with when you have a bunch of these little pixels together, one pixel might come out like this, or one pixel might come out like this. So it's a half a pixel or a double pixel. And when you've got two sprites next to each other, if they don't calculate correctly, the seam, if the seam isn't calculated correctly, and that's because it's like multiplied by 3 instead of multiplied by 2 or multiplied by 4, or say multiplied by 5 or multiplied by 7, what you wind up with would be a perfectly shaped pixel on the right, or along, let's say this is a perfectly shaped pixel. One wide pixel on top, and then one skinny pixel here, and then you've got an area where the video card is saying, I don't see a pixel, even though technically a pixel should be there because the math is wrong, so the video card picks up the background. And I'm going to dub this pixel tearing. Since there's no other term out there, I'm creating the term pixel tearing. So that's when you're talking about programming a pixel perfect image. And the thing is, if you program it correctly and you have a pixel perfect image, what you really have should be, this is going above the thing, but it should be like this. You see that? So they're all together. But what you have when you multiply it by an odd number, you have the background peeking through. If you download my game Punch Hitler until I manage to fix this issue, you will actually see an example of pixel tearing after every odd event of Hitler bouncing toward the center of the screen. And for whatever reason, the math gets funny, and it's weird. And I have tried every mathematical equation I can to reset the bouncing, but whatever it does, it has nothing to do with the distance traveled by Hitler or the time traveled by Hitler. It will always pixel tear where some of the face sprites are sewn together. That's for what's going on right now. Now, there are ways to compensate for that, and that is to have a seam line between the pixels, or like a background image that appears behind the sprites that essentially provides a seam, like an overstitch in sewing, or only this, an understitch, to prevent people from seeing through the seam line, right? You can do that, or you can multiply it by factors of 2 or 4, or you can project. Now, I'm going to talk about the projection thing later. But this is basically a soft introduction to what's going on. And so I covered the TV screens and I covered this. Let me cover TV screens again, because I did get a little off topic. Don't save. So the TV screen, I'm going to discuss it again later. So I'm discussing it a couple times. Oh, come on. Where is it? Where is the... There we go. Bringing back up technology connections. And yes, I'm like pumping them up here, right? I love technology connections. Oh, I'm just gonna keep messing around with this. This does look better. Okay, so when you're trying to portray something on a CRT, what you wind up having to do is you wind up having to either use some sort of filter or shader, or you have to change the way your pixels look when you create your sprites. And you can do it So one of them is mechanically, and when I say mechanically, what I mean is you change how your sprites look directly. And the other, and that would require less processing time but more artistic time. Or you can do it using a shader. Now, I wanted to tell you about pixel tearing because that will absolutely affect any sort of shading you do at a later date. And a shader or a filter, in order to capture a CRT, it would have to do this. It would have to separate the image. So anything in Unity is a projection, right? It's like a surface projection. In fact, in general, if you think about how computer graphics work, they're very much like how a movie works, or how you watch a movie, right? You project an image onto a video layer. This is the most basic fundamental concept of video processing. So I know it's a lot more complicated than that, but if we use simple terms here, you'll be able to understand the concepts a lot more clearer. So you're basically projecting an image onto a video layer. That's basically the most basic way to describe it. Well, for a regular projector, the video image is projected one for multiples of one, like 1 for 236 times, or 300 times, or whatever. And it takes the film and it projects it right onto a silver screen, or rather it is a reflective movie screen, so you could see the image. And that's really important to understand, is that you can do basically the same thing, or what you're basically doing is that very same thing in Unity. And what you want to do is you want to create a CRT version. Now, so in programming Pixel Perfect back in the, for arcades and for home systems, what the vast majority of artists did was they created, pixel artwork is pointillism. So what a lot of artists did was they created pointillistic artwork, knowing that it would be then turned into impressionism. And those are some advanced concepts for you. And the reason why I say that is that the CRT, as you can tell, is not one-for-one for pixels. It's not like a silver screen in a movie theater. You're not projecting a perfect pixel to view. You are zapping rectangular-shaped pockets of phosphor to glow, and the intensity of the glow from 3 phosphorus pockets creates the optical illusion of color. So how do you achieve that? Well, I'll discuss that later. Right now, what I'm going to say is the concept of pixel perfect is highly dependent on the effect that you want to achieve. So if you're going to go for the CRT effect, know right now that you will have to get your pixels as programmed, or pixels to be programmed as perfect as possible. Because then you're going to manually or automatically distort them. Now, if you are using, if you're going to manually distort the pixels, what you can do in Photoshop is you can separate the layers of the pixels into like CMYK. Only you're going to have the yellow layer divided equally into thirds with the blue, green, and red layers. Because, you know, because of something that you're going to wind up doing. Oh, no, actually, you know what? In one Photoshop, I was able to separate just red, blue, and green. So you could do red, blue, and green separation, or you can do CMYK. If you're doing CMYK, remember that the yellow layer you need to duplicate it 2 more times and reduce the opacity by 1/3, and then merge the yellow layer, each yellow layer with each of the 3 colors. Or you can separate red, blue, and green, so you have red, blue, and green layers. And those red, blue, and green layers should always also be partially transparent. The intensity of their opacity equals the intensity of color. And you separate them by just a hair. That will only work mechanically if you blow up your sprites to be much, much larger than 1 pixel for each color. Probably want it to be, like, let's say you're doing a 32 by 32 pixel image. You'll probably want to enlarge that image using bilinear, which is exact. You know, you don't want to make it fuzzy. You'll probably want to enlarge it to be about 320 by 320 or 3200 by 3200. That way, when you separate the layers, you get that separated fuzzy effect. And after you separate the layers, you can either have a 3-layered sprite, which moves across the screen, or you can combine them both for a single sprite. In either case, each layer should be Gaussian blurred just a hair. So that's the basic introduction here to CRTs and everything else. The concept of pixel perfect and how it relates to how you want to show it. The second concept of pixel perfect is very, very simple. It's retro themed. Retro themed just means that you're doing a very, you know, it's like Chelsea and the Seven Devils, or Bunny Must Die, or Crystal Lake, where the pixel art doesn't depend on it being blurred. The pixel art depends on all the pixels looking perfect. And everything is perfectly square. That's literally it. It's retro themed. It's not actually retro. Now, there are also people like me who, and you might be one of these people, you don't really want to blur your pixels, but you're still making the pixels to the limitations of like a Nintendo Entertainment System or Sega Master System or Sega Genesis or Super Nintendo, right? So in other words, you're not retro themed, you are retro, but you're not going to be blurring your pixels because maybe it's too much of a hassle. Or maybe you want to give people the option of activating the CRT filter or shader, right? And Punch Hitler I'm kind of falling in between CRT Pixel Perfect and Retro Theme Pixel Perfect because I don't have any sort of shader on it. But I am going to be looking into a shader pretty soon because I kind of want to make my classic 8-bit and 16-bit games look classic. So that's what I wanted to introduce you to in this first half hour. Though all these concepts and everything. Now I'm going to get into setting it up with Unity. So it's at the 30-minute mark. We should probably put a little tiny marker here for myself. Okay. 2, 1, boom! Marker added. Anyway. So, Now let's do the Unity. Let's look at Unity for a second, and let me go through every single one. So I got my project up here. There are a lot of walkthroughs. All of them are wrong. Now there are two ways you can set up the camera. Two very specific ways. I'm going to show you the way that I have it set up for my Windows, and I'm going to show you the way that I have it set up for my Android. Although mostly because, not because I want to show you how to do it for Android, because doing it for Android is actually you're not really going to be able to do it for Android unless you do something fancy. And I haven't done the fancy thing yet, but I will tell you what the fancy thing is. In general, I just want to show you two very specific settings, two very specific setups. One setup you're not going to see because it breaks the concept. And that's because Unity has broken their whole concept of cameras, canvases, and pixel perfects and everything. Promised I won't bitch about it too much. Okay, so first of all, your sprite. Your sprites need to be set up to be pixel perfect. It's a lot of setup here. It's very simple. Now this sprite is actually the entire thing. It's essentially the resolution of the TurboGrafx 16, 320 by 240. Yes, I know you can get up to 512 by 240 in TurboGrafx 16, but we are focusing on 320 by 240. Obviously, if you're doing Nintendo, you would be doing, or Sega Master System, you'd be doing 256 by 192. If you were doing the Game Boy, it would be 160 by 144. See what I mean? So first of all, you set up your sprite. So all your sprites should have identical settings. Pixels per unit. 1 pixel per unit. Unity suggests 108 units, or pixels per unit. I don't know how that worked. It was supposed to compensate for the distortion of the camera in Unity. You could still find walkthroughs that are 6 years old. Don't do 108. Do 1 to 1. 1-to-1 ratio is what you use. Use that. Pivot point, bottom left. Why is bottom left important? Bottom left is important because you want to focus your camera, your canvas, and every single sprite that you summon into the area in a positive graph zone. And that's because cameras and canvases have a pivot point in the center, and they extend from the center out when you expand them. So what you want to do is you want to change the cameras and the canvas and the sprites and everything so they focus in positive Y and positive X. Otherwise, you're going to have real serious problems dealing with negatives. The only possible reason why you could want to do a negative, and it's really the only possible reason, is if you're creating some sort of globe effect, like a faux 3D space. Or you are doing some mathematical calculations that deal with positives and negatives, and you want to graph it out all out without doing any sort of modifications to the calculations, which in and of itself would be sort of part of doing a 3D globe space, because that's when you're doing those kind of calculations. I suggest against that, unless you're heavy into math. And even then, it might still screw up your sprites. It may not. It might. It depends on how good you are. Secondly, you want to do the wrap mode clamp. Clamp it down so it doesn't wrap. The only thing that should wrap is Bismarcky. And just kidding. Filter mode. Point no filter. Max size, unless you're doing something amazing. If you're doing 8-bit or 16-bit pixels, max size 2048 is going to be more than enough. If you're going to be doing something fancy like making sprites that are 3,000 pixels wide in order to manually capture the concept of the CRT, you're probably going to have a much bigger max size. I would suggest against it, right? Resize algorithm, Mitchell, always Mitchell, not bilinear. Not bilinear. Bilinear will fuzz it up. Format, automatic. Let them identify which form of red, green, blue you have, how many alphas, what the bits are. And compression, none, no compression. That's it. That's how you set up your sprites. You can select all of your sprites at once and set them up all identically like that. Oh yeah, Sprite 2D and UI. Mesh type tight. It's, all of the single. I'm teaching you how to do single, not polygon or anything else. Do single. Next, for the game display and the game view, you pick the resolution of your of what you're doing. This basically sets everything up, your canvas and et cetera, et cetera, et cetera. Pick that. Do not use low resolution aspect ratios. It will screw you up. Now I'm going to go into my prefab section here. See, I prefab everything. Canvas. Set your canvas up. It's always best to set your canvas up to be identical to your resolution. So I have 320 by 240. I'm setting up 320 by 240. Don't mess with these, with the rect transform. Other than this, just use this. Screen space overlay for the canvas. Canvas, constant pixel size. Make sure you have constant pixel size. Pixel perfect, yes. Now, when you click on pixel perfect, it will still have an effect even if you don't have a camera attached to the canvas. Even if you don't have a pixel perfect camera attached to the camera that you don't or may not have attached to the canvas. Select it no matter what. Ignore reverse graphics, yes. Blocking objects, none. Blocking mask, everything. All right, that's how you set up your canvas. Now, if you add component and you add the camera to your canvas, you're going to wind up with a field of view. You see this game view over here? This is what you're going to wind up with. And there will be no way, absolutely no way you can expand your camera. I tried. I couldn't get it working. It's not supposed to do that. It's a bug. Do not attach your camera to the canvas. It's not going to work. Next, main camera. Let's look at the main camera here. Transform. Now, main cameras are 1/2 of the display resolution. So 320 by 240, the camera's going to be 160. All right? That's because cameras extend from the middle out. It expands. See this? I can't even. I wish I could enlarge this right here to show you. Let's see. Does it do it here? Yeah. Okay. I think it does. No, it doesn't. See, it won't even show you on the game display. It won't even show you what the main camera is going to be doing. If you look down here in this little tiny window right here, see how it moves? See how it's offset? Make sure that the main camera is positioned perfectly center. So divide it by 2. 320 by 240, divide it by 2. Divide this by 2. So it's 120. So you have 240, 120. The size of the camera needs to be 120. If you notice, I don't have a pixel perfect camera attached to this particular camera. I'll show you the settings with my other project. Depth minus 10, position minus 20 or minus 10. You know, either one is great for the camera to be, because that way you get the camera will capture everything. Make sure it's orthographic instead of perspective. This is in case you're not using the pixel perfect component, right? Viewport rect. It's broken. Viewport rect will trick you into thinking you can put a higher number half the time. The other half the time, it's limited to just putting in 1. Like if you type 90, it will default back to 1. That's basically it. And viewport rect is really a percentage. It's 0 to 100%. 1 is 100%, 0 is 0%. So it's a float number, so you can put anything in here. Just everything. Oh, see, look at that. It's expanding. This is the offset, right? The X offset, the Y offset. It's just leave it. Leave no offsets. Don't put any offsets for the camera. For the width and height, 1 for 1. Always make it 1. If you see with the main camera, when you're modifying it, you're making it shrink. This would be like a way if you want to enlarge something, sort of. You can modify it in that way, but if you try to make it go above 1, nothing happens, right? I think it's when you have the camera attached to the canvas and you have the pixel perfect camera attached to the main camera, it won't let you go above 1. It should never let you go above 1, no matter what, because it winds up breaking unity. And I think this is what I did when I corrupted my project once. I put it above 1, and it kept trying to calculate things above 100%, even though it shouldn't have, and I wound up having to delete and remake my canvas and my camera and everything, because it would never go back to what I wanted it to go back to. So, clipping planes, near 0.3, far 1000, orthographic, calling mask everything, solid color, background. You could change the background to anything. In fact, it's a lot quicker than making a sprite with the background. Viewport rect, no offset for X or Y, 100% for width and height. That's basically what it's saying. This should be displayed in such a much better manner, because the walkthrough that Unity has confuses viewport here with this viewport, the viewport transform. It's no longer called viewport, by the way. It used to be. So that's basically it. Now you saw that I have attached to this a script. I'll get back to it in a second. Let me talk about the canvas now. Oh, I did already talk about the canvas. That's right. Well, see, this is grayed out. That's because I was showing you the canvas down here as the prefab. When you put the canvas up here in the hierarchy, position 160, position 120, width 320, height 240, blah, 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 blah. this is how it's all determined, and I'm pretty sure position X and position Y is grabbed from the main camera. I keep forgetting how and why it does that, but it does. Scale factor 1, reference point per unit. See everything. When you put it up here in the hierarchy, this is what it winds up doing. Alright. Oh, I do have the pixel perfect camera here in the hierarchy. So we'll go ahead and talk about that. Reference resolution needs to be the same resolution up here. Y resolution, same as up here. So it's 320 by 240 for me. For whatever resolution you want, fix it. Assets, pixels per unit 1. You're noticing that there's a trend here. You should be noticing there's a trend here of the same numbers repeating. In fact, on my other project, when I put pixel perfect camera onto the main camera, this was all grayed out. Like I said, I broke this particular project. I wanted you to see that this particular project is broken. So if you break your project, it will still work, but you might be able to have access to things you were not supposed to have access to, which will really foobar the pixel perfect presentation. It really will. But basically that's it. This is how you need to set things up. Look at the familiarity of these numbers. 120 is the size. The size of the camera is always half the height. Always half the height. Some people say half of the width, and I know they're misspeaking because I misspoke before in my previous attempt at this video, but it's always half the height. And the reason why I misspoke before is because I was referencing a walkthrough. So, now, we're going to get to programming the pixel perfect here. Rod Serling. I wanted you to see this particular thing. Window capture. Add existing. C# code. There we go. All right. Now, I name my things in ways that I can remember. What this probably should be called, instead of Rod Serling, it should probably be called Resolution Governor or Resolution Manager. Governor is, if you're an engineer, you know what a governor is. It regulates what is allowed and what isn't allowed. It's, like the warden or the boundaries or whatever. This is where you're setting your boundaries. Now, this is very important because Unity, in fact, I'm going to bookmark this specific section. For those of you who jumped forward by touching the bookmark, I'm discussing the code that's used to regulate the window or the window frame, the frame of the game, the frame of mind, what you want people to see and what level. If we're going to use the movie theater references, this is the scope of the movie theater screen. For using television, this will be the screen size, the surface size of the television screen. Or the window. You can, anyway. This is basically how you project the image in a way where the player can see it. Or this controls like the size of the projection, is what I should say. So maybe it's not like the movie screen. Well, no, it is. It's both, like the projector lens and the movie screen. So you need system collections system period collections, system period collections, system period generic, and Unity engine. I give it as a mono behavior because I have no reason to do it anywhere else, and I don't use anything other than mono behavior in my scripts because I'm a newbie. But this is all you need to do. You put it in start, don't put it in awake. Awake will not work. I don't know why. Theoretically it should, but it doesn't. Or maybe what I should say is it doesn't always work correctly. So if you can get it to work correctly all the time, all the more power to you. I've just compiled projects with it being in awake, and it's like sometimes it just does not function. So stick it in start. Compatible preset window sizes for pixel perfect presentation are. Now that sentence basically means if you've got like a 4K television and you create a window at 320 by 240, you're not going to be able to see your damn game. You want to be able to see it, but you don't want the pixels to be distorted. Well, Screen.SetResolution is the command. And this is literally times. It's a factor of 4. 12 times 320 by 240 for my resolution, because I'm using the TurboGrafx resolution, 320 by 240. Multiply it by 12, and every single pixel will be the exact same width and height as the pixel next to it. Because it's a multiple of 4. 12 is a multiple, it's like multiple of 4 there. You can also do multiples of 2. However, I've discovered that sometimes a multiple of 2 will give you a thin pixel or a fat pixel here or there. If it's exactly 4, it won't. My guess is something to do in relationship to math and the fact that pixels are square and have 4 sides. Multiply to make sure that they are 4 equidistant sides. So it's multiple by 4. But, theoretically, multiples of 2 should be working all the time because you only really need to add a square, another, a double. If you double the width and double the height, it should work no matter what. Except every once in a while, I wind up with a situation where it doesn't. I don't know why. It shouldn't. It might be just my testing. So the actual command that you're using is Screen.SetResolution. You set the X, you set the Y, and then you have it set to false. Now, I keep forgetting what false is. All I remember is that when I set it to anything but false, it gave me problems. But you know what? I'll go ahead and look just for completion's sake. Oh, that's right. Full screen versus windowed. Yeah, you don't want windowed. You don't want full screen mode at all. So that's why you set it to false. You don't want full screen. Full screen mode will break it. It won't work properly. And there are a lot of reasons for that. It won't work properly at all. And that's because it kind of defeats the whole concept of keeping it pixel perfect. Because it will try to translate the pixels. So, like, let's say the resolution is 4K, right? Well, there's no way that 320 goes into 4000. No way. I mean, it goes into 4000 12.5 times. So what you're going to wind up with is a lot of pixels that are half a pixel wide. And that won't function. It just won't. So if you set it to true, the pixels are going to be deformed. If you set it to false, then the window will be very specifically not full screen, regular window, and everything is in its correct place. Pixels are perfectly square, etc. So this is a conditional statement that detects the screen resolution, and it's screen period current resolution period width. This actually detects the resolution of your monitor. And if you go to the Unity docs are kind of contradictory on this. And when I tried to point that out to the Unity team, one of them got really pissed off with me and said, it just kind of means the same thing. And it's because the guy didn't know how to, he's American, and I'm American, but he's clearly, one of those American types that say, oh, two different words, they mean the same thing because they're similar enough. They have different functions. I can't even remember what the Unity docs suggest that I use, but I remember it is not current screen resolution or current resolution dot width. So this is how you set it up. And you set it up like this so that your project will automatically resize to a view that's most comfortable for your viewer. Now you could also set this up so that the viewer or the player can manually choose how big they want the window to be. Messing with set screen resolution and screen current resolution.width can cause you some issues. So that's why for this particular project I didn't give my players the option to switch. I just picked the most comfortable width for the monitor. And it works. It works pretty well. But again, maybe I'm in the developer mindset of I'm going to choose for the player what's best for them. Maybe I'm thinking incorrectly here. But that's why I set it up this way. You can easily set up a command, a more complex script to allow the player to choose the resolution. But for now, that's what I use. This is my example. Set screen period current resolution period dot width detects your monitor's resolution, or your operating system's resolution. I should say it that way, because your operating system might be running at a smaller resolution than your monitor is capable of running. Maybe you like that. So this detects what is set up in your system settings. Set screen period set resolution, width, height, false, because you don't want it to be windowed. You want it to be windowed, you don't want it to be full screen. This is the command you use. Now I'm done with setting a project up. And you have to attach it to your camera. You don't need to worry about it being a singleton, by the way, because you're attaching it to your camera. If you prefab your camera, it's going to be on every single camera for every single screen. And Unity likes to keep the settings that it was previously told to keep. Technically, you probably only need to put this on the camera in the first scene, right? You might only need to do that. But you can change it from one scene to another to have the screen jump up, especially if you want to create some sort of cool effect. Like if you're doing a horror game. Let's say they're playing the horror game in a window mode, and then you have it switch to full screen, like it's taking over your entire computer. There are any number of ways to mess with people using these settings. This is only the beginning of using the setting, right? The most basic function. You could really use it to screw and play with your player, and hell, you could take a screenshot and then maximize the game without the player realizing that the window has been maximized, and then show things happening to your desktop, to their desktop. That would be really, really funny. It would also mess with players, right? So that's the whole concept here. That's the whole concept of all of this stuff, messing with the screen resolution, how you can use it, how you can use and manipulate what your player sees, what they want to do, and all that good stuff. I may put this in my comments or in the description so you guys know where I'm referencing things. I think I'm going to do that. All right, so let me move on to the theory crafting. And, 101. There we go. So theory crafting on how to make... So I told you all the ways to do it mechanically. Make pixel perfect mechanically. Now I'm going to tell you about the theory crafting related to bloom effects and all that good stuff. So right now, standard Unity programming, what you're really doing is you're preventing the pixels from being visually deformed in a way where when you have two sprites next to each other, you don't want the background to bleed through the seam of those two sprites, right? You also want to make sure that you don't have like a really fat end of a T and a really thin end of a T. Now, you may be looking at this game view and you may be saying, well, Kevin, this looks pretty pixel perfect right now. It kind of is. That's because the game view is the game canvas being projected on something else, and you're looking at the projection. You're not looking at the actual game canvas and the sprites. And when you're playing a game, the way Unity is regularly set up is that concept art, let's say that each of these letters are individual sprites, you would be looking at the sprites being displayed directly on the screen and the canvas without any alteration between you and the sprite. So the game view is using a technique that you can absolutely program into your game. It's a technique similar to what was being developed with the video game Portal. So the video game Portal, it doesn't actually, when you shoot a wall, let me use Microsoft Paint here to demonstrate what I'm saying so you understand the theory crafting to it. Okay. So we're looking at a wall sideways here. This is a really terrible wall. Oh, that's right. Oh, no, that's not. Oh, shoot. Yeah, well, maybe I should be using Paint. I'm not going to use anything else. Oh, look. Shapes. Here we go. There's a wall. So, when you are over here, let me put a little head here. Well, I should have been making a square with shapes. You have your little portal gun. There we go, little portal gun. So, in the game Portal, when you shoot the portal gun to this wall, right? What you're really doing is you're really creating a layer that's a projection of, say, the wall that's in the other room. So let's say you first shot the portal gun in this other room over here, and everything that you see. Oh wait. Here. So the first shot you made was over here, right? So everything you see is this wall that's on the back end of this wall. So this is the back of this wall. So this is the front, and this is the back. And this is a different wall. So you're creating a window that looks from this wall, the wall over to the right, over to this wall right here. And what this is actually just a projection. This right here, this circle, this portal right here is a projection of what this other portal is seeing. So you're actually dealing with cameras. You're viewing through cameras. Believe it or not, that's kind of how the game view works in Unity. But how the game works when you compile it is actually very different. You are literally just seeing this wall with all of the sprites here. Here's a sprite, here's a sprite, here's a sprite. So what you could actually do, oh yeah, and because of that, when you adjust the resolution, or when the resolution maximizes, these sprites become deformed in a bad way, where you could see sprite tearing, where you would see the background between the sprites. So let's say that these sprites are on top of each other. Oh, come on. So if the canvas is perfectly aligned to the resolution of your TV or screen, or your laptop screen or whatever, then you wouldn't see any sprite tearing. You know, it's like, let's pretend these sprites are at edge each other. So it would look like one solid set of sprites. But if, let's say, this TV screen right here is a different resolution than the native resolution of the sprites, then what you're going to have is like I described earlier, an issue where you see like the background, because there's like a gap between the sprites, even though there really shouldn't be a gap, because mathematically they're right next to each other, but also mathematically the sprites can't be, you know, the sprites have to be, or the pixels have to be exactly square, and the computer can't process exactly square on a thing that's not square to the size of the pixels or the whatever. So you get what I mean. Well, if you project, if you have this canvas right here that is perfectly pixel perfect, and then you create a projection of that canvas onto the game view, then this is projected and enlarged up here in a way where the sprites look perfect, because the projection is one solid image. So projection is one solid image of numerous different sprites. Now it still may be a little bit wonky, but if you zoom in or zoom out, they will all fit together. Like if you see this game view right now, I'm zooming in and zooming out, everything looks like it fits perfectly together, right? And you could squint, and if you made a copy of this and like a screenshot of this and put it in Paint and put it at exactly the right ratio, none of the pixels would be deformed. You wouldn't, if you had two sprites next to each other, granted this is one big sprite, but if you had two sprites next to each other, none of them would be none of them would show tearing in a way where you see the background through the seam of the two sprites. So that's one way to handle pixel perfect on an unfriendly machine. And I am thinking about doing that for my Android games by creating a projection of a pixel perfect canvas and a pixel perfect camera and showing that projection to the person. The only problem with that is that your projection changes your interaction between the mouse or the fingers touching it. Hopefully you can see these taps I'm making on the screen. Let's see, can you see the taps I'm making on the screen? Oh, you can't. So I guess it just does not cover that. But let's say I'm tapping the screen where my mouse is, right? Oh, come on, stop it. There we go. Yeah, okay. So you see my mouse, and let's say I'm clicking here, I'm clicking there, I'm clicking there, or whatever. Projections work off of a different set of coordinates. And if you do this projection method to achieve pixel perfect zooming, you are going to wind up having to compensate for the coordinates. And to some degree, I've done that. And I did that in this code over here. Because for whatever reason, it was not... there's something goofy between the mouse and creating punches, right? So let me look and see where I've got that. Let me see if I could find this example. Where did I put it here? Calculator. It's not it. Oh, come on. Oh, come on. I've got to find it. Pardon me for taking so much time. Here we go. Alright, let's see if I can find this. Okay, there it is. Vector, okay, Highlander, it is in Highlander. When I instantiate the left fist and the right fist to punch Hitler, I actually have to use something called the capture mouse position. And I thought so. I thought it was in that script. Oh, it's right here. Oh my god. I thought only I had scrolled down just 1 extra inch. You see this mouse return function? I have to get the mouse position X with screen width divided by resolution width. And this is a real problem because there is a disconnect between the mouse position and the actual position of the sprites on the canvas, or just in, maybe not on the canvas, but in the just where the camera views it. I keep referring to it as the canvas, but it's not really the canvas I'm using. Just the visible area that I want for the game scene. And so I actually had to divide to get the correct number for the fists to appear in the correct location. This may be the same math you need when projecting. You know, creating that little window and the projection. But I seem to remember there may be some other calculation that you have to use in order to make sure that anything that you click on with the mouse is clicking the correct thing. In fact, when you're doing the projection, you may not actually be able to click on certain sprites or colliders with the mouse itself unless you're, you know, doing some fancy math or some fancy conversions. Because with a projection, the sprites wouldn't actually be there. It's similar to mini maps, because mini maps are projections onto the canvas. So if you use a mini map projection or a projection similar to how oh god, you didn't even see that part. Let's see here. There, you got the whole code now. If you use the method used for mini maps, where your mouse clicks a mini map and it actually selects a unit, even though that unit isn't technically on screen, it's a projection of the unit, a projection of the map that's been reduced in size. You know, it's basically the same type of code that you're going to have to be prepared for in order to use. Or the portal example. Although with the portal example, you may actually be using ray casting. I mean, Unity is all 3D, so you're still using ray casting anyway. But you may either be using a coordinate system or you may be using line of sight to get coordinates or whatever. It's a little bit more complex and involved, and you may not want to do that. So I think I also described the CRT shader thing, and this is in general what you have to do in order to create a pixel perfect project. But again, it also depends on how pixel perfect you want it to be. Are you enlarging the pixels? Or are you just leaving the pixels at their normal size and enlarging the game view? Whatever you do, make sure that you have these things in mind. What are you going for? Do you want to prevent sprite tearing, side-by-side sprites that show the background through them? There are ways that you can cover up for that. You can either put a sprite behind it so that the background color remains the same color as the sprite, or you may want to have much larger sprites, etc., 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 etc. It is possible to get pixel perfect. It is possible to get CRT emulation. Newer CRT emulations are better than most. Or that you find that predate anything from like 3 years or more. Take a look at CRTs, TVs. Make sure that you get the right kind of bloom effect. Because that's basically what it is. It's a bloom effect. You separate the colors into red, blue, and green layers. You displace them by like a micron. Then you bloom effect each layer, and you have an overlay of that grid, that net that you saw, at like 50%. That's basically all you need for CRT emulation. And it will kind of blur or bloom your pixels together to get the right effect. So that's like a CRT pixel perfect. You could have non-CRT filter or shader perfect. You could also have retro style pixel perfect, where you're changing the size of the screen rather than the size of the pixels, right? And finally, you could also project the actual pixels onto a secondary canvas like the video game Portal does, or like like you might do for a mini map in a RTS, where it's a projection. Anyway, those are ways that you can handle Pixel Perfect. Thank you for listening to my whole video. I've done everything I can to give you all of the information that I need, or that you may need, that I think that you might need, the information that I need. I can also show you my other project here real quick. It's a project I did a long time ago, and I captured the video, the Game Boy aesthetic. You could also have canvases on top of other canvases, you know, where it's not a projection. That's fun. You also don't need to force the resize not to happen while also maintaining the specific size of the canvas. That's also fun. But you'd have to have a background. And remember, on Android, you may have to have a culling mask. A culling mask, you can do it manually, where it's literally just a giant picture with a cutout in the middle. So, you know, like I did here. This black area is a forced cutout. And that's because that was before I figured out that some people could resize the game. So I put that in there, just to make sure that the window couldn't be resized. And that made sure that nothing was seen beyond this. Let's see, look at the Pixel Perfect camera. I got this set up. Rod Serling Pixel Perfect camera. Oh, you can actually modify those things. That's interesting. Sometimes you can't. A lot of times when I create a Pixel Perfect camera, I can't modify those. They're grayed out. This is one of the things that I've set up here. Rod Serling. This is for a very, very simple project. Set screen resolution. The simplest you can get without needing to detect anything. I made sure that the screen resolution was exactly 640 by 576. And I set it to 576 for a reason. I can't remember what that reason was. But yeah, it's basically what I... Oh, wait. Was that... That's the Game Boy resolution times 4. 144 times 4 is 576. 640 is, so it's 160 by 144. So, you know, the Game Boy was made to be a little bit taller, you know, closer to square than the Nintendo resolution. And I'll also show you my other project, my test project. Let's see here. Just take me 2 seconds. I turned the camera on so you guys could see my face. Anyway, while this is loading up, those are the questions that you need to ask yourself and how you want to approach Pixel Perfect. I mean, what's your definition? What are you going for? And 47, 48, 49. There we go. See, look here. Like I said, there are times where the projection is grayed out. You can't control it. So this is the pixel perfect camera here. Just remember, use the similar settings. Use the same numbers. Unity may throw you for loops. It will always try to throw you for loops. There are functionalities that the main people with Unity don't want to fix, and they never will fix, and they'll just keep breaking them. But that's basically everything that I wanted to show you between my projects. And you also don't have to necessarily have a pixel perfect camera as an attachment to your main camera. Main camera can achieve pixel perfect resolution because it was achieving pixel perfect resolution before the pixel perfect camera was introduced into Unity as a real thing. And I know that because there are walkthroughs dating back to 2011 and 2012 where pixel perfect camera did not exist. And it's like Unity kept half of the functions. And that's also why you can wind up with Unity getting screwed up. Just absolutely screwed up. Even though you think you put in the right numbers. And at that point, you just need to delete the canvas, delete the cameras, make a new canvas, make a new camera, and get right back into it. So that's... Oh yeah, and restart Unity. That's basically my little mini tutorial here. It's an hour and a half because there are a lot of subjects I wanted to touch on. And I hope that you are familiar enough that you can play with it, that you can fix things. And if my settings don't work, one of two things happen. Numbers got goofed up behind the scenes in a way that you can't modify them. You think you're modifying them correctly, and Unity's not recognizing it. That's probability number one. Restart Unity. Remember to restart Unity if that happens. Always restart it. Probability number two, Unity made an update and broke a feature. Probability number three, a gremlin decided to attack your computer. It's probably Stripe, knowing him. Anyway, have a wonderful day, everybody. Love y'all. Bye.